Hello everyone. I shall continue my discussion on damped free vibrations. So in my previous lecture, I introduced you and I also told you how the system looks like and what is the purpose of study, etc. All that I have told you. And by chance, if you have skipped that and attending this class, I advise you to go through my previous lecture and then start attending this. Otherwise, you may not follow and because shortage of time and I also don't want to keep on repeating the previous things. I shall straight away proceed. And I have taken a system, a single degree freedom system, and it is a diagonal system. I have a component, what is called as a damper, okay, and that is also called as dashpot. So a viscous damper is also called as dashpot. So we have what is called as spring, and we have a mass, and we also have a dashpot. This system is called as spring mass dashpot system. Sometimes in short, KMC, K-M-C system. Okay, so I have attached, I have built it, and this mass right now it is stationary and it is in the equilibrium position. And the free body diagram of the mass I have drawn it and it is not moving, therefore I can equate the forces. What are the forces that are acting? One is weight, the mg, and the spring must have undergone some deflection, and delta st, k delta st is the force. And what about the force from this component at this? Please remember, this is a dashpot. The dashpot will offer force only if there is a velocity. If there is no velocity, then it is not going to offer force. The force offered by the dashpot is directly proportional to velocity. F is equal to c into x dot. That's what we have discussed yesterday. Okay, so right now, in this equilibrium position, C component is not offering any force. Therefore, mg is equal to k into delta S. Okay, I would like to set it into vibrations. Let me assume that this mass, I pull it. This is how I start the free vibrations. So when I pull it, I have applied force and I also have displacement. I have pumped some energy into the system and hope that it is vibrating. Hope that it is vibrating. At some instant of time, say this is the position of the mass. So this is at t equal to t. So this is the position. The spring has come up here. The dashpot, this thing also has come up here. And this distance, what I call it as, what is this? This is the displacement, and this mass is also having what's called as velocity. It is also having what's called as acceleration, and let me call these all these x dot, x double dot, they are positive in the downward direction. Okay, so now in this position, in the position at t equal to t, let me draw the free body diagram. Please remember, it is I am not going to apply equilibrium condition because it is in motion m, and I know that it is having x double dot acceleration. It is already having x. Okay, then what are the forces that are acting? The spring, which is trying to pull it up. Okay, so that is equal to k multiplied by whatever the extension of the spring. So in this position, what is the extension? It is not only x plus delta st. That is the total extension, because in this position also the spring has already undergone an extension of delta st. So this delta st plus from here to here another position, another x, delta st plus x, that is the spring force. And what is the effect? What it tries to do? It tries to, the spring has extended, this end is fixed, this end tries to go back. So therefore it tries to pull up the mass, whenever it is upward direction. And what about the component, this dashpot component? Now I know that this mass is having velocity, or the other end, this end is having velocity, and therefore that component, that force, the force offered by the dashpot is c into x dot, and that also tries to pull it up, because any resistance, it is a damper, and the force from the damper always opposes motion. This mass is moving in this direction. What is the opposition for that? There must be a force in the opposite direction. Therefore, that also is opposed. So, in addition to this, what you have is the energy, the weight. Please remember, it is not stationary, therefore you cannot apply equilibrium condition, apply what is called as Newton's second law. What is Newton's second law? Sum of all the forces in the direction of acceleration. Okay, let me start with this. I have what is force mg. Then this force, it is minus k into x plus delta st. This force. And this force is also opposite, minus cx dot. These are the sum of all the forces in the direction of acceleration. E is equal to what is called as m into x double dot. This is Newton's second law. Now I would like to simplify this. This is mg expanded minus k into x minus k into delta st minus c into x dot. E is equal to m x double dot. So I shall cancel this force and sorry, not this one. So what is remaining? This kx is there. So I shall take this force and this force to the right hand side and rewrite the equation. And this is mx double dot plus cx dot plus k into x is equal to m. Don't forget what is x double dot. X double dot is acceleration, x dot is velocity. It is as well as, okay, this in short we have written it as m into d square x upon dt square plus c into dx by dt plus k into x equal to 0. This is now the meaning of this equation, the same thing. So this is differential equation and therefore this also is a differential equation. Both of them are one and the same, expressing it in different ways, that's all. Okay, so what is the order of differential equation? What is the order of? So I have d square x upon dt square. This shall decide what is the order of the differential equation. So in any differential equation, so to what is the highest order of differentiation, that shall decide what is the order of differential equation. So this I say that this is what? Second order. This is what called as second order differential equation. So I also wish you can spend about half an hour, 1 hour at the most on the solutions of differential equations which you have studied either in 3rd semester or 4th semester. I wish you to recall it. Okay, if you can do it, that's fine. But whatever is necessary for us and whatever you had studied, that I shall pick it and keep on telling here. Okay, that I will be doing, but I shall not go in detail why we arrived at, what are the why, the reason for that, etc. I shall be skipping it. Okay, second order differential equation. What is the meaning of this? The meaning of this is, what is the observation? The general solution. The general solution. So this is the word which you definitely must have come across in the study of differential equation solutions. The general solution shall have two constants. Because it is second order differential equations. The second shall have two constants. So those constants can be found out using what are called as initial conditions. Two constants, and these can be found out. What are those constants? How much are those? Found out using initial or boundary conditions. Initial conditions are different, boundary conditions are different. Please remember. Okay, initial conditions. I think that is better, that's sufficient. So initial conditions. Initial means with respect to time. I have here t means time here. Time is varying. So what are the initial conditions? When t is equal to 0, how is the system? They are called as initial conditions. Okay, so using initial conditions, so those constants can be found out. Probably I am not very sure whether you have understood this completely or not. I am not very sure. But anyway, if you are not understood, if you still have doubt, anyway I shall be coming back to this again when I need it. Okay, as I would like to continue. Yesterday I mentioned that I am not going to be happy with the derivation of the differential equation. In fact, that is the beginning of our analysis. So I have got differential equation. In case of undamped system, that is the end of the solution, end of the analysis. But here it is not. It is the beginning. Okay, I am interested in knowing what is called as what is the solution of this equation. What is the solution of this equation? Okay, so I have no idea what is the solution, but I just wish to try. Okay, so whether this can be something, this can be a solution of this. Okay, so what I want to try? So try, please remember, I also have no idea, I am trying. Try x equal to e raised to st can be solution. Can be solution. Solution of what? Solution of this differential equation. Solution of the above differential equation. I want to try it. Okay, so if it is, then before I substitute these things, I shall calculate. I require x, I require x dot, I require x double dot. Therefore, what is x dot? X dot is equal to s into e raised to st. Please remember, s is a constant, t is a time, e is exponential. Exponential st, e raised to st. S is a constant. X dot is equal to e raised to st, and x double dot, differentiate it once again. It is s square into e raised to st. Okay, differentiation of this once again. So this is what? Okay, x is this much, x dot is this much, this is. If this is the solution, when I substitute here, then this also must be satisfied. Therefore, I would like to substitute both things. What is that? M into x double dot, m into s square into e raised to st. So I shall take a bracket, m s square e raised to st. So e raised to st, I shall write it separately. The first term, m s square into e raised to st. Then plus c into x dot, plus c into x dot. X dot is what? Yes. C into s into e raised to st. E raised to st has been taken outside. Okay. Plus k into x. X is what? E raised to st. That has been taken outside. So ms square plus cs plus k into e raised to st. What? This must be equal to 0. If this is the solution, then this condition also must be satisfied. Okay, so here I have two terms, one term within the bracket, the other one is outside. Okay, and that must be equal to, the product of the two must be equal to 0. So either this term within the bracket must be equal to 0, or e raised to st equal to 0, or both must be 0. Okay, so now I know that e raised to st is never 0. E raised to st can never be 0. So if both of s and t are 0, then e raised to 0. What is e raised to 0? That is 1. Anything raised to 0 is 1, that we know. So therefore, whatever may be the values of s and t, e raised to st is never 0. So e raised to st is never equal to 0. Therefore, if that is not 0, if this is not 0, then what must be 0 to satisfy this? Therefore, ms square plus cs plus k must be equal to 0. So ms square plus cs plus k equal to 0. Then what is s? So it is a quadratic in s. Therefore, I shall find out what is the solution of x, what is the value of x. So s is equal to what? This is minus c. That is ax square plus bx plus c is equal to minus b. That. So minus c, this is minus b, plus or minus square root of b square, that is nothing but c square, minus 4ac, that is 4mk, the whole thing divided by 2 times a, that is nothing but 2. Okay, so once you take minus sign, the other time you take plus sign, and you get two values of s. Therefore, I shall call it as s1 and s2. S1 is smaller than s2. Therefore, whenever I take s1, I shall take minus sign, and whenever I am talking to s2, I shall take plus sign. Okay, s1 comma 2, I shall rewrite it, separate it, minus c upon 2m. So this 2m I am separating it, plus or minus square root of. So this 2m no, that I am taking within the square root. If I take a 2m within the square root, what it becomes? It becomes 2m whole square. So if you have something, say 1 by 5 into say 30. So I want to take this 5 inside. So what is this? This is equal to 30 divided by what? It is 5 square. So if you want to take outside the square root 5 square, then it becomes 1 by 5. Just like that. Here also I have 2 by 1 upon 2m. 1 upon 2m I would like to take within the square root sign. So therefore this becomes, so c is already there. This 2m, then this is square. C square divided by 2m whole square. The same thing I have written it as c divided by 2m whole square minus what? 4mk divided by 2m whole square. That is nothing but 4m square. So 4 cancels, 1m can cancel. So this I shall rewrite it. This is equal to minus c upon 2m plus or minus square root of c upon 2m whole square minus k by m. So the moment hearing k by m, do you feel anything? Okay, you should start feeling. You should feel. We have discussed so much about undamped free vibrations, string mass system. Okay, so that is nothing but omega n square, or omega n is equal to root of k by m. Okay, what is omega n square? That is nothing but k by m. So k upon m is nothing but omega n square. What is omega n? Omega n is undamped free vibrations. Undamped free vibrations. This is equal to omega n is equal to root of k by m. Therefore, omega n square is equal to k upon m. Okay, this is the reason why we wrote that. This. Okay, I hope it's clear. Minus c by 2m. This. Yes, 1 comma 2. Yes, 1 comma 2 is equal to. What is S1? If you want, you only S1. S1 is equal to minus c by 2m minus square root of this. And what is S2? S2 is equal to minus c by 2m plus square root of this. Okay, I hope it's clear. Okay, now I have something. I shall come back here. What is C? What is C? We call it as damping coefficient. This is called as damping coefficient. So it is a constant for a given system. C is equal to, if you remember in yesterday's class, so C equal to mu into A divided by P. What is mu? Mu is the viscosity of the fluid. And what is A? A is the area, cross-sectional area of the plate. The area of the plate which is in contact with the fluid. And what is T? T is the gap between the fixed plate and the moving plate. Okay, so all these for a given damper, for a given dashpot. So this A, T, okay, probably I had shown you what is A and what is T. So for a given dashpot, usually you can't change it unless you change the piston, cylinder, etc. But this mu you can easily change, no? Mu you can easily change. You change different value of mu. So by changing the value of mu, I can change the value of C. I have the freedom of changing the value of C. Okay, suppose I want to change the value of C. Okay, I don't really do it by changing the oil. I want to imagine it. Okay, I want to imagine. What is the imagination? I want to change the value of C to what is called as CC. I want to change the value of C from C. I would like to change it to CC. Imagine what? C is changed to C suffix C. Okay, so what is that suffix C? We call it as critical. CC, we are going to name it, call it a little later, critical damping coefficient. Okay, critical damping coefficient. C to CC. Okay. So what is the value of CC? The value of CC is such that the term within the square root sign now that becomes 0, such that square root of C is changed to CC divided by 2n whole square minus omega n square is equal to 0. So it is only an imaginary thing. I have changed the value of C to CC, and the value of CC makes this term equal to 0. Makes this term equal to 0. And that value of C which makes this term to 0 is called as critical damping coefficient. So how much is that value, etc. I am going to find out. Okay, so now I can, since 0 is on the other side, I square it both sides. So when I square it, then it becomes CC divided by 2m whole square minus omega n square is equal to 0. Or in other words, let me write down here only, this is equal to omega n square. Or in other words, let me take the square root, CC divided by 2m is equal to omega n. Or CC is equal to 2m into omega n. Very important. What is the value of critical damping coefficient? Its value is equal to 2m multiplied by omega n. For any system, it shall have a critical damping coefficient and its value is given by 2m into omega n. Maybe I can further simplify. Cc is also equal to 2m. And what is omega n? Omega n is root of k upon m. This can also be written as 2, this m and root m. I cancel and I have what called as root m into root k. This can also be written as 2 root k into m. This also is equal to 60. Okay, the moment I know this system, so I know what is the value of k, I know what is the value of m. So without doing all this, I can easily find out what is the value of Cc. What is Cc? Cc is equal to 2 times square root of k multiplied by m. That gives me the value of Cc. So for any given system, you know what is k, you know c, you know m. You also know what is the value of Cc of that system. I hope it's clear. Cc value is known to you. Cc value is known to you, and that is given by this. Okay, so I would like to proceed further. So please remember this equation. Okay, I would like to simplify this. Let me rub this and okay, I had slightly deviated after getting this equation and went slightly in the other direction, and I introduced a term to you now. What is that term? Critical damping coefficient. How much is critical damping coefficient? Okay, so now I shall introduce you one more term. Please see how I have written it. This is called as, this is read as zeta, Z-E-T-A, zeta. So what is this? What is this term? This is called as damping ratio. I am going to define this as damping ratio. Damping ratio. What is this? This is equal to C by Cc. C by Cc. What is damping ratio? Damping ratio of a system is the ratio of the actual damping coefficient to its critical damping coefficient. Okay? This C is what is called as the actual damping coefficient. And for this system, I can also find out what is Cc. What is Cc? Cc is 2m omega n, or Cc is 2 into square root of k into m. So I can easily find out what is the value of Cc. So then I can find out the ratio of C upon Cc. And that value is called as damping ratio, and that is denoted by zeta. So zeta is called as damping ratio. Okay, so now I have something. So small manipulation, I should say. C by 2m. So from where since I have a term here C by 2m, C by 2m. So whether I can replace C by 2m in terms of zeta, that's what I am trying to do. Okay, C by 2m, can I write it like this? C by Cc multiplied by Cc by 2m. Nothing else. Multiply and divide this term by Cc. Numerator and denominator. Cc cancels, and what is remaining is C by 2m only. Nothing else. So what is C by Cc? What is C by Cc? C by Cc is what? Zeta. C by Cc is zeta. And what is Cc by 2m? Somewhere here. Cc by 2m. Cc by 2m is what? Omega n. So that means C by 2m, wherever is there, I can replace it by what is called as zeta into omega n. So wherever C by 2m is there, I shall replace it. Wherever means here. I have here and I also have here, and simplify this. So all this is very, very mechanical. Please don't lose contact. Please follow along with me. And if you have anything doubt, any doubt, you can definitely ask me. Okay? I shall come back. I shall come back to this now. Yes, 1, 2. So yes, 1, 2 is what? Yes, 1, 2. The first one is C by 2m minus C by 2m minus zeta into omega n. C by 2m, we have just shown that it is same as zeta omega n. Okay, plus or minus square root of C by 2m whole square. Okay, that is the thing, but zeta square into omega n square. C by 2m is zeta omega n whole square, zeta square omega n square, minus what? Minus omega n square. So this I can further simplify it. This is nothing but here I have omega n, here I have omega n, here also I have omega n. So first within this square root I take omega n square outside, then I take it outside, it becomes omega n. So what I mean is I can write omega n here. So this is equal to minus zeta plus or minus square root of zeta square minus 1, and this is equal to yes 1 comma 2. Most important. This will be our starting point for our further analysis. Yes, 1, 2. Please do not forget what we started. We got mx double dot plus cx dot plus kx equal to 0. That is the equation of that motion, differential equation. Then I wanted to know what can be the solution of that. So then I said x equal to e raised to st. Why can't be this solution? That is my starting point. I substituted in the differential equation and then simplified, and that is the answer. If this is the solution, then these are the values of S1 and S2. As I said, this will have two constants. Okay? and therefore this is what we call it as S1 and S2. What is S1? Take minus sign here. What is S2? Then take plus sign. We will have two values of S, and that's what. Okay, before I proceed, now I have found out the value of zeta. What is zeta? Zeta is the ratio of the actual damping coefficient to the imaginary, what is called as critical damping coefficient. Imaginary value. An imaginary value of damping coefficient is called as, we are calling it as critical damping coefficient. How much is its value? 2m into omega n, or 2 times root of k into m. Okay, so if zeta is greater than 1, that is, when the zeta is greater than 1, C must be greater than Cc. That is, C is greater than Cc. The actual damping coefficient is greater than critical damping coefficient. Okay? So if this condition is satisfied by a system, then that system is called as over-damped system. That system is called as over-damped system. Okay, this is one of the, so this let me call it as A. Then I have another condition. If zeta is equal to 1, that is C is equal to Cc, then that system is called as critically damped system. This is called as critically damped system. The system is critically damped. The damping is same as critical damping coefficient, and that system is called as critically damped system. So here I am just taking K, C, M. So depending upon the values of K, M and C, I can find out what is the value of Cc. Then I compare Cc and C. Then this system may be over damped, this system may be critical damped, or possible, third possible. What is that? If zeta is less than 1. If zeta is less than 1, what is the meaning of that? C value is less than Cc. C value is smaller than Cc. So this system is called as, under damped system. So very important, a system which is damped, so that is classified into any one of this. It is not that every system can be classified this. You have a system, you know what is its K, M and C, you know its Cc, and compare the C and Cc, then find out whether the system belongs to this or this or this. It belongs to any one of the category. Okay, so I am going to stop here, and by just telling that, I shall show that this system and this system shall not induce free vibrations. If the system belongs to this category or this category, then the system shall not have free vibrations. You can have free vibrations only if that system is under damped system. Okay? So I shall show you, I shall prove you, and each case I shall separately discuss and then continue a longer discussion for this case. All the best.